Hello students, today we are going to see some more interesting and important questions from Narendra Avasthi sir's physical chemistry, redox reaction, level 2. Come on, let us discuss few more questions from this session. Here the first question, 20 ml of 0.1 m solution of a compound Na2CO3, NaHCO3 2H2O is titrated against 0.05 m HCl. XML of HCl is used when phenolphthalein used as an indicator, and the YML of HCl is used when methyl orange is used as an indicator in two separate titration. Hence, Y minus X is. So we have to identify the volume of HCl for both the reactions. So that is a separate titration. No. So this is first and foremost Na2CO3. Here, Na2CO3, Na2CO3 dot NaHCO3 2H2O. It is a double salt. Right now here, first in that first titration, Na2CO3 plus HCl. You will get what it is? NaHCO3 plus NaCl. So that means the reaction is not completely finished. So this is actually what it is. XML they are using, right? XML. So in that, phenolphthalein is used as an indicator to identify the reaction whether it is completed or not. That second step, that means the second reaction, NaHCO3 plus HCl. You will get what it is? NaCl plus H2O plus CO2. Right now here, methyl orange is used as an indicator. Here, YML is used. So now we have to identify that volume of HCl, how much we are using for these. Okay, I just bring that idea for you to understand what purpose we are using, what is that idea about the indicator. Indicator, why do we use? Whether the reaction it is completed or not. So that is the purpose we are using. Right now here, Na2CO3 plus HCl, we are adding phenolphthalein as an indicator. When you add phenolphthalein indicator, it is a colorless. When it is in acidic medium, it is a colorless. Okay, when it is in acidic medium, it is a colorless. But as that ml of HCl, XML of HCl, drop by drop when you are adding and the reaction started, so you will get the pink color when it is completely reacted. That means the reaction it is completely filled. So here actually what is the pH range of phenolphthalein? 8.3 to 10. So in that pH scale 1 to 7 it is a acidic solution, and 7 to 14 it is a basic. So 1 to 7 it is a acidic, no, but here 8.3 that means it is a basic. So when it is turning into a base only, you are getting a pink color. And the same way, so that means the first reaction which is not completely finished, so it is incomplete, right now. And the same way, second reaction, methyl orange is used as an indicator. So methyl orange, when it is in acid, it is a red in color. So what is the pH range? 3.2 to 4.4. So when it is completely finished, it will change into yellow. That is what I just to bring that idea for you. Neutral pH, methyl orange, same, remains the same as it is. It is an yellowish color. But in acidic pH, it is red in color. So that is what acid, it is red in color. And the same way, base also, it is red in, yellowish in color. So that means methyl orange is a basic indicator. Phenolphthalein as a acidic indicator. I hope you got that idea. When it is in base, pH is same as it is in that birth color. That means neutral color. When it is in acidic only, it will change. And the same way, phenolphthalein, acidic, it is a colorless, but basic, it is changed the color. So when it is changed the color, that means the reaction it is completed. Please remember. Okay, come on. Why I'm giving this ideas and all, even this also they may ask the question, which is used as an acidic indicator, which is used as basic indicator. What is the pH range? How do we identify? So these are the points you please note down. That's what purposely I just mentioned. 1 to 7, it is an acidic point. 7 to 14, it is a basic point. So 8.3 to 10, it is a pH range. So naturally it is a basic. So that means when it is turned to basic color, that means this is used. Phenolphthalein is a weakly acidic solution. And what it is, methyl orange, it is a weakly basic. So where there is strong acidic, so naturally weak base only it will be. Okay, come on. Let us go and identify the data and finding the answers. So here 20 ml of what it is, 0.1 m, 0.1 m solution of the compound. Okay, so here we have to find out the molarity. So here Na2CO3, NaHCO3, 2H2O. This is a mixture. So they have given what it is, 0.1 m molarity, and volume it is 20 ml. So moles of Na2CO3, moles of Na2CO3. So moles of Na2CO3, we can go in this formula, molarity into volume of solution in liter. Okay, so molarity, it is what they have given, 0.1 m. Into volume of solution in liter, it is 20. No, so 20 we can convert it into, see, 20 ml. We can convert it into liter. It is 0.020 liter. So here 0.020 liter. So you will get that Na2CO3 moles, how much it is? Here actually 0.002 moles. Right. Now here in this point, volume of HCl. So volume of HCl, what indicator we are using? Phenolphthalein indicator. Volume of HCl. Volume of HCl in that XML, right? So here what we are using indicator? Phenolphthalein indicator. Phenolphthalein indicator. Right. Right. Now here, let us identify the moles here. Actually, Na2CO3. So here XML of that moles. So this here volume of X. Volume of X, that is HCl. How do we calculate it? Moles by molarity. Molarity. So moles, how much we got it in that Na2CO3? Here 0.002 we got it. Divided by molarity, in the question it has mentioned 0.05, right? Here in the question 0.05 m HCl they mentioned, no? Okay, now here let us apply 0.05 m HCl, and this is moles. So you will get what it is, volume of that HCl of X. So you will get what it is here. You will get what it is, 0.040 liter, right? Because here moles we mentioned in the liter only. No, this we converted into liter. So here we can mention liter only. So volume of HCl of XML in the first reaction, when we are using phenolphthalein indicator in the first reaction. I hope you got that idea. So Na2CO3 plus XML of HCl, you are getting NaHCO3. That point you are getting 0.040. That is the volume of HCl of the first reaction. Now we have to identify the volume of YHCl. Volume of YHCl. So how to identify this? For that, what indicator we are using? Methyl orange indicator. Methyl orange indicator. Right, so here methyl orange indicator, so the reaction, it is completely neutralized, both the carbonates and bicarbonates, right? So the required HCl, so the required HCl. So how much actually? Here 2 HCl required to complete the neutralization. Here now you see the reaction. Here one HCl and here one HCl. So 2 moles of, well, balancing equation, 2 moles of HCl we required. So that means here, according to balanced equation, it is 2 moles of HCl required, and while calculating 0.002 moles of HCl it is required. So naturally the required HCl, it is actually 0.004 moles required. I hope you got that idea. Okay, now total HCl. Now total HCl moles. Total moles of HCl. Here 0.004 plus in the reaction what it is, 0.002. So you will get how much? 0.006 moles required. So here actually required is this one. Why we are going for required? Because in that reaction, how many HCl we are using for? Completely neutralized. For that 2 HCls required. And actually while calculating, you are getting 0.02 mole HCl. So you will get what it is, required HCl. Now totally combined together, moles of HCl, you are getting 0.006 moles you are getting. Now, volume of Y we have to identify. How to identify volume of Y? Volume of Y. So that means HCl only, right? So volume of Y, it is moles by molarity. Moles. Always volume means it is moles by molarity. Molarity. So moles by molarity, it is 0.006 divided by molarity. How much? What is the molarity of HCl? It is 0.05 m. This is mole and this is molarity. So what is the answer you will be getting? You will be getting around 0.120 liter you are getting. So that means here 120 ml. We just converted into ml because in the option they mentioned ml only. So now Y, it is actually volume of HCl. It is Y actually how much? 120 ml. That means X how much? So Y minus X we can go for it, right? Y minus X. If we go here 120 ml minus here how much we are getting actually? The next question, a sample containing HASO2 Arsenous acid, molar mass it is 108 gram per mole and weighing 3.78 gram is dissolved and diluted 250 ml in a volumetric flask. In that 50 ml of sample liquid is withdrawn with a pipette and titrated with 35 ml of 0.05 m solution of iodine. Calculate the percentage of Arsenous acid in the sample. Right now we have to identify the percentage of the sample. Right now HASO2 Arsenous acid. Here what they have given that point. Here in that Arsenous acid they have taken 3.78 gram and dissolved in 250 ml in the volumetric flask. So what is the molar mass of Arsenous acid? It is 108 gram per mole, right? Now in that dissolved content and the diluted dissolved content, 50 ml as titrated against 35 ml of 0.5 m iodine solution. So what is the molarity of iodine? 0.05, sorry, 0.05. Here 0.05 m iodine solution and titrated against what it is? 50 ml of, that is actually what it is. They have taken that the sample 3.78 gram dissolved in 250 ml of the volumetric flask. In that 50 ml they have taken also this liquid titrated against this. Now we have to identify the percentage of that Arsenous acid. You know percentage of that Arsenous acid, how to identify? They have given all these data along with this picture I have explained. Come on, let us check how to identify. Right now here Arsenous acid HASO2 combined with iodine with water. So you will get what it is? H3ASO4 plus 2H plus 2I minus. Here balancing actually here 2 you will get it. Here you will get 2, right? Yes, is it balanced? H3. Yes. Right now here in that 1 mole of HASO2 reacts with 1 mole of iodine. Right. Now we just check all the data so that it will be easy for us to identify the answer. Now volume of I2. Volume of I2, it is 35 ml. See, you just check this data I have given in a easy way for you to understand. So here 35 ml of 0.05 m I2, right? Iodine solution. And the same way molarity of I2, that is actually 0.05 m molarity. Now moles of I2, you know moles of I2, how do we identify? Molarity into volume in liter. So you will get how much? Come on, let us apply the value. Molarity 0.05 m into volume 35 ml. No, we just converted into liter. It is 0.035 mole. Here actually liter only we just mentioned. No, we did not converted into ml. So here volume of HCl X equal to 0.040 liter. We just converted into what it is ml. So this is 40 ml. I hope you got that idea. Volume of X ml, the first reaction. Now volume of Y ml, that is HCl. So this is second reaction. Now here in this point, here we just mentioned 40. So here 40 ml. I hope you got that idea. How do we get that 40 ml? The first one. Okay, now how much you are getting? Here you are getting 80 ml. So y minus x, it is actually 80. Now y equal to 120 ml, x equal to what it is 80, oh, sorry 40 ml, 40 ml. So y minus x equal to, you are getting this answer. So y equal to 120 ml, x equal to 40 ml. So here y minus x equal to 80 ml. I hope you got that clear idea about this question. Right, come on, let us check the answer. Here, what is the answer you are getting? I hope you got that idea. How do we analyze this? This is a little bit lengthier because I wanted to give a clear idea about indicator also. That is what I just bring it to your notice. Now, which is the correct option? Option B is the correct option. Yes, come on, let us go to the next question. The next question, a sample containing HASO2 Arsenous acid, molar mass it is 108 gram per mole and weighing 3.78 gram, is dissolved and diluted 250 ml in a volumetric flask. In that 50 ml of sample liquid is withdrawn with a pipette and titrated with 35 ml of 0.05 m solution of iodine. Calculate the percentage of Arsenous acid in the sample. Right now, we have to identify the percentage of the sample. Right now, HASO2 Arsenous acid. Here, what they have given that point, here in that Arsenous acid, they have taken 3.78 gram and dissolved in 250 ml in the volumetric flask. So, what is the molar mass of Arsenous acid? It is 108 gram per mole. Right now, in that dissolved content and the diluted dissolved content, 50 ml as titrated against 35 ml of 0.5 m iodine solution. So what is the molarity of iodine? 0.05, sorry, 0.05. Here 0.05 m iodine solution and titrated against what it is? 50 ml of, that is actually what it is. They have taken that the sample 3.78 gram dissolved in 250 ml of the volumetric flask. In that 50 ml they have taken also this liquid titrated against this. Now we have to identify the percentage of that Arsenous acid. You know percentage of that Arsenous acid, how to identify? They have given all these data along with this picture I have explained. Come on, let us check how to identify. Right now here, Arsenous acid HASO2 combined with iodine with water. So you will get what it is, H3ASO4 plus 2H plus 2I minus. Here balancing, actually here 2 you will get it. Here you will get 2, right? Yes, is it balanced? H3. Yes. Right now here in that 1 mole of, here 1 mole of HASO2 reacts with 1 mole of iodine. Right now we just check all the data so that it will be easy for us to identify the answer. Now volume of I2, it is 35 ml. See, you just check this data I have given in a easy way for you to understand. So here 35 ml of 0.05 m I2, right, iodine solution. And the same way molarity of I2, that is actually 0.05 m molarity. Now moles of I2, you know moles of I2, how do we identify? Molarity into volume in liter. So you will get how much? Come on, let us apply the value. Molarity 0.05 m into volume in liter. It is actually 35 ml, no, 0.035 liter. So we just convert into liter, right? So 0.035. So you will get that moles how much when you calculate this? You will get how much? Yeah, here 0.035 0.00175 mole. I hope you got that clarity. So moles of I2, we got it. Now we have to identify the what it is, mass of that sample, right? Okay, so mass of that mass of HASO2. Okay, now here molar mass, how much? Molar mass they have provided, right? So molar mass of HASO2, how much? 108 gram per mole, right? Now here in the equation what we observed here, 1 mole of HASO2 reacts with 1 mole of iodine. So that means that reaction 1:1, the mole ratio. So here also we got that moles, how much? Moles of iodine, it is actually 0.00175 mole. So the same thing we can identify here also, because that mole 1:1 ratio, no? So this also moles of, I just mentioned here, moles of here, moles of iodine is equal to moles of HASO2. So the same mole can be applied over here. So the moles of HASO2 is equal to 0.00175 mole. Okay, so molar mass of HASO2, this one, and the moles of this also same. Now can we apply that value for to identify the mass of the aliquot, that is given sample, right? So given mass of the aliquot, that is HASO2, what they have provided in the question. Right now here, mole into molar mass. So we will get what it is, given mass. This category you know very well how to identify the given mass. Mole into molar mass. Mole, it is here. Molar mass, I just bring it over here. So can we apply the value here? 0.00175 mole into molar mass 108 gram per mole. So when you calculate these two, you will get 0.189 gram. This is gram because it's a given mass. I hope you got that idea. Yes. Now we have to go for total mass of aliquot. Okay, so total mass, because they have taken 250 ml, and then in that 50 ml they have taken, right? See here in this picture, I think you will come to know. So this they have, what is the sample gram? 3.78 gram, which is dissolved in 250 ml. In that 50 ml they have diluted with the 250 ml. In that 50 ml they have taken for the titration with iodine solution. Right now here total mass we have to identify, right? So here total mass of HASO2, total mass of HASO2. HASO2 also same, Arsenous acid also same, aliquot also same. Okay, now that is equal to mass in aliquot. How much it is actually here? Mass in aliquot into 250 ml divided by 50 ml. Right. So 250 ml divided by 50 ml. Now here in this point here, given mass, this much is right. So 0.189 gram into 250 ml divided by 50 ml. Right. 50 ml. So how much you will get? Total mass of that Arsenous acid when you calculate it. So you will get how much total mass? Here you will get around 0.945 gram. So when you calculate this, you will get 5. No, when you calculate this, you will get 5. So 5 into 0.189 gram. So you will get 0.945 gram. I hope you got that idea how to calculate this point. So here from 250 ml, in that 50 ml they have taken. No, so that is the reason I just put it. Okay, now we are going to see the percentage of the sample. So the percentage of HASO2 in the original sample, right? Sample, how much gram they have taken? 3.78 gram. In the picture it has mentioned, no? 3.78 gram, right? 3.78 gram. 78 gram. Okay, so now percentage of HASO2 equal to total mass of HASO2 HAS O2, areneous acid, no, capital A, small s, divided by sample mass, mass of the sample, mass of the sample, mass of the sample, this, original mass is this. Okay, can we apply the value? Percentage means it is 100, right? Enter 100. So here, what is the answer? You will be getting 0.945 gram divided by 3.78, 3.78 gram divide into 100. So you will get how much? It is 25%. So the answer, it is 25% they have taken. Yeah. So what is the answer? I hope you got that idea. It is lengthier question. I hope this picture will help you to understand this. Right now here, what is the answer? Here in this question, option, it is A is the correct option. 25%. You are getting, yes, answer also 25 only. Yes, answer it is 25%. Yes, come on, because while calculating and we are getting the correct answer, but while checking, I mean, while getting the answer, while writing in that, we will put that wrong. That is what I wanted to verify. It is 25%, right? Now I just bring that idea for you. See here, this is another way of calculation. You just note down whether this also, it may be useful. For me, I have given clear idea for you to understand. So that is what I have taken a lengthier point, how to go for each and every step. This is very simple, but still, if you are able to identify this also fine. This also, you're getting this step. This method also, it is easy only. I hope you got that clarity. Come on, let us go to the next question. I hope you understand this point, this question, right? Come on. The next question, a mixture of FeO and Fe2O3 is completely reacted with 100 ml of 0.25 m, that is molarity, acidified KMnO4 solution. The resultant solution was then treated with zinc dust, which is converted to Fe3 plus, that means ferric ion, of the solution to ferrous Fe2 plus. So the Fe2 plus required 100 ml of 0.10 m K2Cr2O7 solution. Find out the weight percentage of ferric oxide Fe2O3 in the mixture. So actually, we have to identify the mass percentage of ferric oxide. Here, the mixture of ferrous oxide and ferric oxide completely reacted with 100 ml of 0.25 m acidified KMnO4. Okay, come on, let us write the ion equation. That is potassium permanganate, right? So that means acidified, acidic medium. So let us identify the N factor. From that, we can go for the calculation part, right? MnO4 minus, so when we go for H plus ion for that, Mn2 plus. So how many oxygens are there? That many water molecules. So how many hydrogens are there? That many H plus ions. Right. Okay. So how many electrons exchanged in that? Here plus 7 2 plus 7 2, here plus 2. Right. So that means how many electrons exchange? 5 electrons exchange. So that means number of electron change, it is 5 electron. So N factor, it is 5 electron. Right. And the same way here, ferrous to ferric. So here in this point, Fe2 plus, which is converted to Fe3 plus. So here in this N factor of Fe2 plus to Fe3 plus, here it is 1 electron. Exchange of electron, it is 1 electron. Right now here, equivalence of KMnO4 we have to identify. So equivalence of KMnO4. It is actually how to identify volume into molarity into N factor. So equivalence of KMnO4, how to identify? So equivalence, generally equivalence, how to identify? Volume, molarity and N factor. So volume of KMnO4, it is 100 ml, and molarity of KMnO4, it is 0.25 m, and N factor, it is 5. Right, 5 electron. I hope you got that idea. Now, here, what is the answer? So, you are getting 125. So, 125 is the answer for ml only, right? So, milli electron volt, sorry, milli equivalence, right? Milli equivalence. So, now millimoles we have to identify. So, millimoles of millimoles of what? FeO, because that is a mixture of FeO and Fe2O3, right? So now let us identify that FeO. So this is millimoles of FeO. How to identify? So milli equivalence divided by volume of the solution, that is 1000 ml, right, into what it is, n factor of FeO, that is FeO, Fe2, what it is, Fe2 plus converted to Fe3 plus, right? So that is 1 electron, right? So that means here 125 divided by 1000 ml into 1 electron. So what is the answer you will be getting? You will be getting around, you'll be getting 0.125 mole. Whose mole is that? This is FeO moles, right? Now the next one, it is actually total Fe2 plus is titrated with zinc dust, right? So here total Fe2 plus, I just mentioned this information also. Total, then total Fe2 plus is titrated with zinc dust, right? Zinc dust. Right, now here Fe2 plus valency, it is 1 electron. Valency factor of K and O4 we have to identify. Now, sorry, K2Cr2O7, K2Cr2O7. So K2Cr2O7, Cr2O7, 2 minus. In the same way, acidic medium, right? So that means here Cr3 plus. So Cr3 plus, plus how many oxygen? That many water molecules, 7H2O. How many hydrogen? That many H plus ion. So that means 14H plus ion. And how many electrons exchange? Here actually how many electrons exchange? Here plus 6, which is converted to plus 3. So that means here for one chromium atom it is 3. So 2 chromium atoms it is 6. So n factor it is 6 electrons. Okay, now equivalence of K2Cr2O7, the same way we can go for to solve. So equivalence of K2Cr2O7. So what are the points we have to go for it? So that is volume into molarity into n factor. Okay, volume, ml only, volume into molarity into n factor. Right, so volume into molarity into n factor. So volume, it is actually how much? It is 1000 ml into molarity 0.1 m into n factor 6 electrons, right? Got it? And the same way, so you will get how much? So you will get how much? 600, right? 600 milli equivalent. Now the same way millimoles, right? So millimoles of Fe2 plus. Again, it has converted to what it is with the zinc dust, right? Fe2 plus to Fe3 plus. So I just mentioned Fe2 plus, right? Okay, now here the same 600 divided by 1000 ml into what it is, Fe2 plus to Fe3 plus, that is 1 electron, that is actually n factor. So you will get how many millimoles? Here you will get 0.6 moles. So 0.6 millimoles only, right? Okay, now next one, here we have to identify the difference, right? So how to identify the difference? Here moles of Fe from FeO, that means ferrous oxide, how much? 0.125 mole, right? And the same way moles of Fe from Fe2O3, moles of Fe from Fe2O3. So how much you are getting? This is 0.6 mole. So let us identify that final difference here. Both. So here 0.125, no, first one. Okay, 0.6 minus 0.125 mole. So you will get what it is, 0.475 mole. That is the difference for both, right? Now here actually Fe2O3 and FeO, both 2 atoms are available. Ion, it is 2 atoms are available. So moles of iron is equal to 0.475 divided by 2, since it is 2 atoms are available, no, iron. So that is, here you will get what it is, 0.2375 moles you will be getting of Fe iron. Now we have to identify the given mass, then only we can go and identify the percentage mass. So both are mixtures, no? So molar mass of FeO So molar mass of FeO, how much? It is 56 and 16 here, 71.84 gram per mole. Right. I hope you got that idea. How do we get that finalized answer about that number of moles of each atom, and how do we get this mole, and then finally we are bringing this mole and divided by 2. I hope you got that idea. Yes, come on. And now here, because this is a mixture, no, so we have to separate it. The same way, molar mass of Fe2O3. So you will get the same Fe2O3. So 159.69 gram per mole. Right. Now here, given mass we have to identify. So given mass of FeO, how much? Moles into molar mass. So FeO moles, how much? It is 0.125 moles into molar mass. It is here, right? 71.84 gram per mole. Right, now you will get that usually moles into molar mass, you will get that given mass. That idea you know very well, right? Okay, so you will get the answer here. So 8.98 gram, right? The given mass, it is that much only, gram, there is no more. Given mass, no. Okay, now the same way, given mass of Fe2O3, given mass of Fe2O3, the same way, moles into molar mass. So how much here? Moles, actually, here 2 atoms are available, as I mentioned. No, here 2 atoms are available. Here Fe2O3. So for that is the reason we divided by 2, right? So here moles 0.2375, right? 2375 into molar mass 159.69 gram per mole. Right, now altogether how much you will be getting? You'll be getting 37.93 grams. So this is a given mass of Fe2O3. Right, now both the mass we have to see the amount, sum. Right, now total mass of FeO plus Fe2O3. Right, that means here what it is? 8.98 gram plus here what it is? 37, right? 37.93 gram. So we will get totally 46. How much? 46.91 gram. Right, now we have to find out that what it is, mass percentage of actually what it is, Fe2O3. Now this is a total mass. This is a total mass combined together. Now mass percentage mass of Fe2O3. So here Fe2O3, this is Fe2O3, right? So 37 here, mass of given mass of Fe2O3 divided by what it is, total mass. Right, this is the total mass, right? Okay, now into 100. Okay, so when you calculate this point here, 37.93 gram total mass divided by total mass 46.91 gram into 100. Right, now here what is the answer you'll be getting? Around 80.85%. Actually, mass percentage of Fe2O3 is 80.85%. It is very long sum, but I hope you understand. The answer, it is option A, 80.85. Option A is the correct option. I would like to introduce another step also, another method. So here, this is the method from the book, what they have provided. So milli equivalents of both, that as I mentioned, here the same thing, they too are provided. It is not much difference. Here also the same. Yeah, here actually divided by 1000 ml I just mentioned, but directly they have given. And here this also the same idea what they have provided, and final result, it is this only. Yeah, I hope you got this. Is 38 by 38 plus 9. So here actually I just bring that idea about what it is, same idea only what they two brought it, but it is very lengthier what I brought it. I hope you understand, right? Come on, let's go to the next question.